Hi, and welcome everybody. It's really exciting to see all of you from so many different places. Okay, as you've seen, technology today is not sufficient. We need something more advanced, like quantum computers. So I'm going to tell you today about the quantum information revolution. I want to explain what's the connection to quantum, and how do you build computers out of quantum mechanics that rely on quantum mechanics. And I want to tell you why they're so exciting. Now, I have to stand here, so unfortunately I cannot move, so I hope you can see me in this corner. Okay, so quantum computers is a very, very young field. It's something like, well, it's actually not that young. It's already 20 years old, but it's really in its beginning. And the subject of this field are computers that don't exist yet. They are computers that rely on the laws of quantum mechanics, and we currently are trying to build them in tens of laboratories all over the world. There are billions of dollars that are invested in the attempt to build those computers. And the reason why so many people are so interested in these computers, both from the theoretical aspect and the physical aspect, is because if we will manage to build those computers, we will be able to do things that currently it will take the lifetime of the universe to do. For some problems, they will provide exponential speedups. So our solutions will be exponentially faster than the current regular computers can do. So I want to tell you today a little bit about what these computers are, why they're interesting, how we can define those computers, or how we should think about them, and what are the open questions that, if you want to think about this direction, you might discover new things about them, and how they also give insight to other areas in science. Okay, now I'm happy to take questions also during the talk, because this is a very difficult subject, especially if you haven't learned about quantum mechanics. How many of you have taken a course in quantum mechanics? Okay, so a few, but if you haven't heard about quantum mechanics or haven't really learned it, it is somewhat difficult, and I'm really happy to answer questions during the talk. And since the subject is so interesting and so deep, and we can talk about it for a really long time, it doesn't matter if we cover everything in the talk. It matters to me more that you understand what we're talking about. Okay, so quantum mechanics is a very funny theory, right? I think you've all heard, even though you haven't taken a course in quantum mechanics, about Schrödinger's cat, right? Is there something that you've heard about? Yes. Yeah. Okay. So in this conference as well? No. Okay. So Schrödinger's cat is this Gedanken experiment, an experiment in thought that Schrödinger came up with in 1935, 80 years ago, and in this experiment, this cat gets into this metal box, and there is some cyanide bottle inside the box, and then photons can come and hit a detector outside of the box, and if a photon hits the detector, then some hammer drops on the bottle breaks, the cyanide breaks, and the cat dies, unfortunately. And otherwise, if the photon doesn't hit the detector, the cat stays alive. And because the photon is a quantum particle, the cat can be in a superposition, that is a combination of being both dead and alive at the same time. And this is something that Schrödinger came up with, actually, in order to say that quantum mechanics is a very paradoxical theory. It cannot be true. And indeed, you don't see around you cats that are in superposition of both dead and alive. But if we could isolate the cat enough from the environment so that it's really, I mean, a cat is a live thing, so it cannot be isolated completely. But if we could, then we would have been able to see a cat which is both dead and alive. And I will talk later about what's the exact problem. Okay, so quantum mechanics is already 80 years old. Yeah, actually more than almost 100 years old. Now, in 1936, 1 year after Schrödinger's cat experiment was invented, Turing, do you know this guy? Turing. So Turing invented his Turing machine. I think it was 1936. And the Turing machine is a model for computers. And however, it took something like 60 years almost to connect the two things and to think about quantum computers. Okay, so Feynman and Deutsch are basically the inventors of quantum computers, and but they haven't really, well, actually Feynman hasn't really specified the name quantum computers or the model of quantum computers. He just thought about the idea, and then Deutsch defined quantum computers, and still only maybe 2 or 3 people in the world were thinking about this. And it didn't really seem interesting enough for people until something really exciting happened. And do you know what that is? Have you heard about it? Huh?
Factorization.
Yeah, the factorization algorithm. So Peter Shor, in 1994, came up with an algorithm for solving the problem of factorization. You're given an integer, and you want to find the factors, the integer factors of that integer. Why is that so interesting? So he managed to find an algorithm on a quantum computer. Of course, you don't know what that is yet, but I'll explain to you later. He managed to find an algorithm that does it efficiently. Efficiently, meaning in polynomial time, in the size of the number of digits that you need to write the number in. Okay, so we managed to do that very, very fast. Assuming you have a quantum computer. Okay, why was that so interesting? Do you know why? Why?
The algorithms are working using the fact that the really large integers are really hard to factorize.
Exactly. Yeah. So what Peter Shor basically said is, give me a quantum computer and I will be able to break the cryptosystem RSA. And RSA is probably the most common cryptosystem used. So everybody got extremely excited about this and extremely worried. And governments wanted to go to use these, well, actually government wanted to build quantum computers first so that they can crack cryptosystems first, and that's the main reason right now why people are actually investing money in quantum computers, because of the RSA. However, this is not the only reason why these computers are interesting. These computers are interesting because, well, if you can crack RSA, if you can solve factoring much, much faster than any other classical computer can do, then maybe we can do other things. So the challenges that we're facing right now in this field is, first of all, physically realize those computers, then discover what else can be done with those computers. And finally, the whole field sheds new light about physics, because it talks about physics from a computational point of view. And talking about physics from a computational point of view gives it a different perspective. So many, many new directions open up. Even if quantum computers are never built, it's still interesting because it opens up new questions about physics, and it's already opened up many, many other interesting things. So that's the third challenge. Okay. So, okay. Do you know about the two-slit experiment? So some of you yes, and some of you don't. So I'll go over it pretty quickly. The two-slit experiment is probably the best way to explain the principles of quantum mechanics. And for me to explain to you what quantum computers are, I have to explain to you what are the basic principles of quantum mechanics. So the two-slit experiment has three different parts to it. One is the classical part. You have some cannon shooting balls through a wall with two slits, and there is something behind it that counts how many balls hit at every point. And you collect how many balls hit at every point, and you sort of draw a histogram. And if one slit is closed, then the histogram will be a bell-shaped, in front, where the peak of the bell is in front of the open slit. If the other slit is open, then the peak of the bell will be in front of that. And if the two slits are open, well, the cannon just shoots the balls, and the balls will pass through both slits, either here or here, and so we will have, the histogram will be a sum of the two histograms. Okay, so this is what we'll get. Now, if we do it with water, with waves, then the analog experiment we'll have a pool with very, very shallow water, and we initiate waves in one side of the pool, and then we let the water pass through two slits, and we measure the intensity of the waves. That is the difference between the height of the water to the average height of the water. And you can see that if one slit is open, we see a peak like before, but if the two slits are open, we see what you all know, interference pattern. Okay, and I think you all know the third part of the experiment. When you do it with electrons, which you might think of as particles, you get, what do you get? The interference pattern. Okay. So, and this is interesting because it's hard to explain how to get interference pattern. If you think of an electron that either passes through one slit or the other, then how come that in a place where if one slit was open, the electron passed, you opened another slit, the electron no longer passes through that place? How come? It's hard to explain. Okay, so now if you measure this, if you put some light and measure whether the electron passed through one slit or the other, you indeed see that it passes through one slit or the other, but the interference patterns disappears. Okay, so I want to extract the principles. I just wanted to review this because for those of you who don't know, I want it to be our basis. Now I want to extract the principles that we need for quantum computers. And those principles will be very simple. The superposition principle and the measurement principle. The superposition principle, what does it say? It says as follows. It says that if you have a classical system that can be in two possible states, say a spin a magnet that can point up or down, then the classical system can be in a linear combination of these two states. It can be both up and down. So it looks like that. For those of you who know about vectors, we describe it by assigning to it a vector in a vector space of 2 dimensions. So, and these funny notations are simply Dirac notations for vectors in a vector space. So the general state will be some combination of the up and the down. The up and the down are the basis states of this vector space, and A up plus B down means that you have some weight A in front of up and some weight B in front of down. Okay, so in general you have something like this. If the red vectors correspond to up and down, the basis, the orthonormal basis of the vector space, then the yellow vector is some general vector pointing in some general direction. Okay, so, okay, are there questions about this? Some questions? Because, yeah.
Yeah, what exactly do these signs mean?
What exactly what?
Do these signs mean?
You mean the notation like this? Yeah, this is a notation of a vector. It's just a notation of a vector in some vector space. So that's all. So this with an arrow pointing up means one vector, and this with an arrow pointing down means an orthogonal vector to it. Okay. And A and B are just complex coefficients. In fact, you can think of them as real coefficients. Okay. So you have some vector pointing in the vector space, and it's in a general direction. So basically, the quantum system doesn't know where it is. It doesn't know if it's pointing up or down. Okay? Yeah. So this is great for spins. It's already very counterintuitive for spins, but here is my attempt to draw a cat who's both dead and alive. And even the cat can be with some weight dead and with some weight alive. And a door can be both open and closed, so it also can be in a quantum superposition if it is isolated enough. Okay? Okay, and yeah.
What do you mean isolated enough?
Isolated enough. So, okay, we'll get to it in the end of the talk, but if the system is not interacting with the environment, then the environment doesn't measure it, and then the system can be in a superposition. Okay, so this is how the Schrodinger's cat can be both dead and alive. It's actually in some vector corresponding to some space that one of its basis states is dead, one of its basis states is alive, but it is in some general state. Okay, now this is very counterintuitive, but for now, let's believe it. Okay, now, okay, so the system, yeah.
Excuse me, why you mention superposition? Does this just mean only one state, or it means 10% possibility to be open, 10%, 90% possibility to be closed?
Yeah, okay.
Is this one position or method?
Yeah, good. Very good question. So, does it mean that if I go back, the question was does this superposition, say A is 10% and B is 90%. Actually, we'll see that it's not 10% and 90%, but it should be a square root of 10% and square root of 90%, so that the norm of the vector, the length of it, is exactly 1. But never mind. It's some number here, some number there. So does it mean that we have both this possibility and that possibility, or some combination? What does it mean? So I have to tell you to be careful here. This is not like what happens with a coin, right? If we throw a coin up and we don't look at its state when it fell, we also think that it's with probability half up and with probability half down, so it's in some superposition of up and down, right? It sounds the same, but it's very much not the same. Why is it very much not the same? Because even though we don't know whether the coin is up or down, the coin knows. Somebody knows. There is a reality. There is a realistic state. Maybe we didn't look at it, but it exists. Here, there is no state. The state is really, at the same time, up and down. And only when we measure it, it decides. Okay? And we'll talk about it later. We'll talk about it in the next slide. So what happens when we measure it? So, okay, we have a system that didn't decide if it's an up or down. It's in some combination. But still we want to measure and see if it's up or down. So what happens? Quantum mechanics tells us, this is the second principle, the measurement principle. Quantum mechanics tells us that the answer is probabilistic. The answer is unknown to anyone, not even to the particle itself, before it happens. And once it happens with some probability. It will either be up or down, and it will be up with probability which is a squared, and it will be down with probability which is b squared. Remember I told you that the length of the vector needs to be 1? This is why I said that the 10 needs to be squared of 10 and the 90 needs to be squared of 90, because their square needs to add up to 1, because this is probability. Okay, so the system decides, the particle decides somehow whether it's up or down. And once it decides, the system now changed, and it has become whatever the result of the measurement is. It's either up or down. So let's repeat it. When a particle is measured, the answer is probabilistic. The superposition collapses, changes, the state of the particle changes according to the superposition, and it basically just falls, projects itself either on up or on down. Okay? And this is something, you know, you probably, even if you haven't taken a course on quantum mechanics, you must have heard about the debate about quantum mechanics and the fact that it's very, very counterintuitive. And you already see these are the most counterintuitive principles that you can think of. Both things are both dead and alive at the same time. And then when you measure them, nobody knows how it happens, but one of the results come probabilistically. And the measurement actually changes the state of the system. Okay, so this is very, very counterintuitive, and Einstein spent his last few decades of his life to try and find an alternative theory for quantum mechanics, because he really didn't like the idea that, well, there are many, many ideas that he didn't like here, but the one idea that he really didn't like is this idea that I demonstrated before, that if I have a coin and I flip it, the coin knows what it is. Someone in the universe knows. Maybe I don't know, but someone in the universe knows. So there is reality. There is realism. Something in physics is realistic. And in quantum mechanics, you don't have this reality. The reality is fuzzy, sort of, until you measure it. Okay. So there's a famous saying of Einstein that you must have heard about, you know, God doesn't play with dice. And this is Born answering Einstein, saying, you can't tell God what to do. Okay, so even though quantum mechanics is so counterintuitive, still, as far as we know, for the scales we measure it and for the experiments that we have performed, it works extremely well. Now, quantum mechanics has been tested in tens, maybe hundreds of thousands of experiments in many, many different directions. And you can't actually imagine the 20th century without quantum mechanics, for better or for worse. Yeah, I mean, there are bad things that came out of quantum. I mean, the quantum mechanics is there. We can use it for good or for bad. And but the effect of quantum mechanics of the discovery of quantum mechanics was unbelievably strong on the entire evolution of the 20th century, on the technological revolution. The invention of lasers, the invention of transistors, which led to the invention, to the internet, to the technological revolution, has all come through the discoveries of quantum mechanics. Okay, so this is quantum mechanics. Now I want to see how to connect it to the information era. How do you take quantum mechanics and talk now about information processing? Okay, so elements of quantum information, like in classical computers where we have bits, in quantum computers we have quantum bits or qubits. We call them qubits. And those qubits interact between themselves in a way which classical bits cannot interact, and it is called quantum entanglement. So this is what I want to explain next. Okay, so we have a two-state quantum particle. This is its two-state, and we can think of these two states. Okay, so we don't know yet how quantum computers, how quantum bits will be physically realized. We have no idea. But for this talk and for thinking about it theoretically, it doesn't matter. We want to think of the two-state quantum particles as some elementary information unit. Okay, and I want to think of one of the states as 0 and one of the states as 1. just like a bit in a computer. And quantum bits can be in superpositions of 0 and 1. Okay, so let's replace this up and down by 0 and 1. Okay, now if this wasn't weird enough, now we're going to get weird. Okay, so quantum entanglement. Quantum entanglement happens when you take two quantum particles and put them together. And when you take two quantum particles and put them together, let's see what the superposition principle tells us. Okay, we go back to we only use these two principles. So the superposition principle tells us that the state can be in any linear combination of the possible 4 states, right? A system of 2 qubits can be in 4 possible classical states: up, 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 down, down, up, and down, down. And so there are 4 basis states in our vector space. Its dimension is 4. And so any linear combination of these 4 states is okay. So here is one of these states: 0, 1, minus 1, 0. Okay? And you can check that the norm of this state, the length of it, is really 1. 1 over square root of 2 squared is half, and minus 1 over square root of 2 squared is also half, so the norm is 1. Okay, so why is this state so weird? Okay, the state is very weird because basically, suppose you have 2 parties, Alice and Bob. We'll meet them again later. And Alice holds the left qubit, and Bob holds the right qubit. You see, the left qubit is represented here by, it's written A down there. So this is the state of the left qubit in one of the members in the superposition. 0, 1, this is the first member. Minus 1, 0. So if a basis state, if we were not in a superposition, if we were in a basis state, then the state will be either 0, 1 or 1, 0. But now we're in a superposition. So the first particle, the particle of Alice, doesn't know in which state it is. It's either in 0 or in 1, and it doesn't know where it is. And the second particle, the Bob's particle, the right particle, also doesn't know where it is. It's either in 1 or in 0. Now, what's funny about it is that what's weird about it is if Alice now measures her qubit. So let's go back to the measurement principle. What happens if Alice measures her qubit? Well, sorry?
Or knows. One side knows.
Bob knows, right. So if Alice measures her side of the system, meaning her qubit, then according to the measurement principle, what happens is that she will get 0 with probability half, and she will get 1 with probability half. I didn't actually tell you how to measure a system with 2 qubits, and I just want to measure 1 qubit. But the rule is the same like measuring 1 qubit I said before. The rule is just, you get the answer 0, 1 with probability half. You get the answer 1, 0 with probability half. So if you measure 1 qubit, you just look at the left part. So when Alice measures her side, she will see 1, for example, with probability half. But if she sees 1, the state has collapsed to the state that agrees with 1. So now, what will Bob see? If she measures 1, what will Bob see? 0. So Alice knows what Bob holds. If she measures 0, she knows Bob has 1. So this looks like Alice and Bob can transform information in any rate, in any, however fast they want. Faster than light, for example. Yeah?
How do you entangle 2 quantum particles? How would you make them be connected to each other?
Yeah, that's a very good question. How do we entangle? How do we create this state?
Yeah, I mean,
right? So this depends very much on the system. But for example, if you take two particles that which have interaction between them, have some a magnetic field that they are both inside the same magnetic field, and you can somehow modulate it so that the energies of the different states, different basis states, will be such that each one will be separated. And then by acting somehow on those energy states, you can entangle them. Yeah.
How fast it is?
How fast is it? To do what?
To like if you measure something and it will pass the other thing. How fast it is?
Oh, okay. So immediately. It's not. I mean, it doesn't have time. It happens immediately, and the reason why it happens immediately is because basically, when Alice measures, it's not that something really happened to Bob's state. Physically, Bob's state remained the same. It still remained with probability half 1, probability half 0. It didn't really affect it. It's just that Alice knew. Let me give you an example, okay? It will be much simpler. You can have the same effect also classically, and there it's very simple. Okay, so suppose, what's your name? Elad. Okay, and what's your name? James. Okay, so suppose I prepare now two boxes. In one box, I have, well actually I have balls, not boxes. I have either two pink balls and two blue balls. Okay, and I just randomly pick from my balls, and I either send Elad and James a blue ball and a pink ball, or I send Elad and James a pink ball and a blue ball. Okay, so it's one of two possibilities: a pink and a blue ball, or a blue and a pink. Now, Elad can be in Australia and James can be in India, and when Elad will open his box and see the color of the ball, he will know the color of James' ball as well, right? So this has nothing to do with actually affecting the state. It's just the action of knowing. Yeah?
How do we know that in the quantum example that when you get 0, the other side gets 1? What's physical law guarantees that?
Well, basically the principle of measurement guarantees that. The measurement of one qubit in a system of 2 qubits says that the state will collapse on the basis state, on basically the eigenspace that is spanned by all states that start with 0. So here it will just collapse on 0 and 1. I guess I didn't answer your question. So can you ask it again?
What I mean is we get 0 at one quantum bit, we observe it and we get 0. And isn't there the possibility that other side got 0 too?
No. So in this state, no. Because we only have the possibility of 0, 1 and 1, 0. So if Alice measured 0, the state has collapsed to this state. Okay, so somebody asked here, and correctly, well, if this happens classically, then what is, how do we know that it doesn't happen, that it's not the same quantumly, right? So, what's the difference between quantum and classical here? Okay, so the point is that indeed the correlations that I told you about, the fact that if Alice knows, I ignore this alphabet. The fact that if Alice knows her state, she also knows Bob's state, etc., this can happen classically. But the difference is that in the quantum world, if you know, well, the difference is in the quantum world, you can have this effect in all bases at the same time. Okay, so let me explain this. Okay. Yeah.
Just quickly, this is all in like a binary system with 0, 1. Can it happen in like a
like 3-dimensional state?
Yeah, everything can happen in all dimensions. Yeah, I just took the simplest thing. With 1 dimension, it's not interesting, but anything above 2. Yeah. Can you please raise your voice? Can you please speak up?
The dimensionality, you told the dimensionality is 4. So why not 0, 0?
Okay. It's true that if we have two qubits that can be in the state 0, 0, 0, 1, 1, 0, and 1, 1, they can be in any combination. So they can be in the state, for example, 1/2, 0, 0, plus 1/2, 1, 0, 1, plus 1/2, 1, 0, plus 1/2, 1, 1. This is also a valid state. But the EPR state is a special state. Okay? This is a very special state that has this entanglement properties. Many states have this entanglement properties, but the EPR state is a particularly interesting state. Okay, yeah.
As you know, the particle is in multi-places, and then one of the options disappear, instead of nowhere and then one option appears.
Yeah. Okay, I'll have to answer this later. Okay, once we get to quantum gates, etc., it will be easier to answer. Maybe ask this at the end of the talk in the questions part. Okay, so yeah, so what I said is that the difference between the classical system and the quantum system is that the quantum correlations can happen in all bases. What do I mean by that? When I talked about measuring a quantum bit, I explained how to measure it just measuring 0 and 1. So I talked about a system in which, say, this is 0 and this is 1, and I measure if it's here or here, and if I have a general state, then it collapses either here or here. But in fact, I don't have to measure in this basis. I can measure in a rotated basis. I can also measure in the blue basis. For example, this, this is, you won't see it, in the orange basis. This and this. Okay? And in this basis, the system will collapse, will be projected deterministically. There is no probability. It will just be projected exactly on this vector, because it's exactly in the direction of the vector I'm measuring. Okay, so for a general direction measurement, say this direction, the state that I have, the state will just be projected with probability which is cosine theta squared here and cosine of this theta, that is sinus theta squared here. Okay, so it's just projected on one of the two basis states, and it doesn't, I can measure in any basis. I can rotate the basis. Okay, so the beautiful thing about the EPR pair is that if I measure in the regular basis, we call it the computational basis, the 0-1 basis, Alice knows exactly what Bob will have if she knows what she has. But this also happens in every basis. This is a little exercise you can do, that in any basis, also in the plus-minus basis. So plus is defined to be 0 plus 1 over square root of 2, and minus is defined to be 0 minus 1 square root of 2. So they're rotated, they're sort of the orange basis. And also in the orange basis, if Alice measures in the orange basis and she gets plus, she knows that Bob has minus. So in every base, they are sort of tied together. Now I meant to bring a toy to demonstrate it, but I forgot to bring it. Do you know this little wooden toy where you have pieces of wood tied to each other by strings, and you open it up and then it goes click, 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 and then you open it up in a different direction, it goes click, 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 and do you know this?
Yeah.
Some of you know and some of you don't. I wish I have brought it. So entanglement is something like that. Whatever direction you look at it, the two particles are tied together. Okay, so now why is this surprising? What can you do with it? Okay, so as I told you, Einstein looked for a long time for ways to replace quantum mechanics by a more reasonable or intuitive theory. And basically he you can say that he was an advocate. He supported the idea that there should be a hidden variable theory for quantum mechanics. What does it mean, hidden variable? It means that even though the system maybe can be described by all these funny vectors and notations and all that, underlying it is a simple description that looks classical. Like, it's as if he imagined as if every particle has in its pocket a list of the answers to all the measurements that can be asked. And the answers are not probabilistic, they're deterministics, okay? And only when the particles meet and get together, they can exchange information about each other. So he imagined a theory which is both local and realistic. Like the coin, that knows what its state is, no matter. The coin knows if you measure me, I'm up or down, but it knows. Okay, so Einstein wanted the world to look classical, to look intuitive. And 30 years later, it was essentially proven that Einstein was wrong. So, I'm sorry?
I've never heard that sentence before.
Well, okay, there's always the first time. Okay, so even just for that, it was worth it. Because it's we're all, even Einstein can be wrong. So actually there's a way to explain it for physicists, and then there's a way to explain it with a game. I will explain it with a game, okay? So it's called Bell's game, and Bell invented it, essentially. And the game works like this. Okay, the guy on the left is called Alain Aspect, and during his PhD, he proved in an experiment that he actually showed that that one can distinguish experimentally between whether Einstein is wrong or right, and he showed the wrong side. Okay, so the game goes like this. Alice and Bob can meet and discuss things between themselves, and then they go apart, and they never talk to each other until the game is over. Okay, at the beginning of the game, they can come and meet and discuss things, and discuss about strategies, etc., and then they separate. Okay, and now what happens? Alice is given a random bit, XA. It's either 0 or 1, and it's completely random. Bob is also given a random bit, either 0 or 1. And now Alice has to write down her bit A. Okay? Now all she knows is what she's discussed with Bob before the game started, and the bit that she was given, XA. And she has to write down a bit, little a. And Bob too has to write down a bit, little b. Now, when do they win? It's not a game between Alice and Bob, it's a game between Alice and Bob and someone else, a referee. Alice and Bob win when, according to the following rules. If the bits that they received are Alice got 0, Bob got 0. Or Alice got 0, Bob got 1. Or Alice got 1, Bob got 0. Then they win if A is different than B. It's a bit complicated, but once you digest it, it's easy. Okay? So in those three cases, they win if the bits that they write are different. Only in this case, when they both got 1, okay, good, turn off? No. When they both got 1, they win if the 2 bits are the same. Okay, so now what is their best strategy? What should they do? Wow, okay. What is their best strategy? We started very, very late. Ah, so it does, oh, you should have told me because I haven't gotten to quantum computers at all. Okay, I'll tell you in a moment about quantum computers. But, so what should they do?
They want that the best probability for them is that A doesn't, not able to be. So they should choose that.
Yeah, so their best bet is to choose A different than B without even looking at their bits. And then they win with probability 3/4. And it's actually very simple. It's a little exercise to show that they can't win with more than 3/4 probability. Now, if they instead remember that quantum mechanics is also possible to use, then what they will do, this is a proof that they can't win with probability more than 3/4. If they remember about quantum mechanics, they actually can share an EPR pair. When they meet, they create an EPR pair. However they do that, it doesn't matter physically. And then Alice takes her particle, Bob takes his particle, and then what happens is that they can measure their qubits according to different bases, depending on the bits that they received. If they received 0, Alice, if she receives 0, she measures in the regular basis. If she receives 1, she measures in a slightly rotated basis. If Bob receives 0, he measures in the regular basis. If he receives 1, he measures in a slightly rotated basis, but in the other direction. And if you do the calculation, because of those correlations, they actually win with a larger probability. Now, they win only with probability 0.85 or something like that. But still, you can show that no matter what, any classical explanation cannot explain this 85%. So basically, this experiment shows that the world behaves with no explanation which is classical. We have to neglect the intuition of classical physics. Okay, so now I want to give you a glance of how you use these principles for quantum computers. How do you make quantum meet Turing? Okay, now the reason why quantum computers are so interesting is because of what happens with all these principles I told you about when you make not 2 particles meet, but n particles meet. When you make n particles meet, according to the superposition principle, how many states how many combinations can they be in? 2 to the n. 2 to the n for even 100 particles or 500 particles is 2 to the 500, which is more than the estimated number of particles in the universe. And a general quantum state can be in a superposition of all those 2 to the 500, or a general quantum state of n particles is some state in this enormous, gigantic space. So that's a general quantum state. And this is a huge difference between classical and quantum systems. Classical systems can be described by linear number of coefficients. Quantum systems require 2 to the n, exponentially many coefficients to describe a general state. Okay, so this difference is what makes quantum computers really unimaginable. I mean, this is the dimension in which the computer lived is just gigantic. So Feynman in '82 suggested to use those systems, the quantum computers, the quantum systems, for a quantum computer. Now, why is that reasonable to use? So the reason Feynman thought about this idea of, or thought about actually connecting quantum mechanics to computers is because if you have a quantum system with many particles, because the dimension is so large, because the number of coefficients you need to write the state is so large, you cannot actually write down the state of a very small system. If you have 100 electrons, the general state of 100 electrons, to write the state down, there's just not enough space. Well, 500 electrons, there's just not enough space in the universe. So it seems like those systems have inherent capabilities inside them. They somehow do things, very small systems, somehow do things that are very, very complicated. And if they do things that are so complicated, it must be that if we cannot simulate it, if we cannot do what they can do, it may be possible to use them. Instead of trying to simulate them, we can use them as computers. Okay? So rather than trying to guess what they're doing, if they're so complicated, maybe we can just use them as computers. So basically, quantum computers are quantum systems of many, many quantum particles that we are able to control carefully. Okay, so I don't have time to explain to you what can you do with quantum computers at all, but I want to say one last thing before I go to the blah, 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 blah. Before I go to the, okay. Let's just do this slide. So this is one thing you can do with quantum algorithms, which is the factoring algorithm. So, okay, let's do this quickly. We have 15 seconds to solve this problem. The left side of the class solves the left problem, and the right side of the class solves that problem. Huh? But you're not allowed to give me an answer, one or... Done? I know you got the easy side. But actually, usually what I get is an answer from this side first. Because those who get the easy side don't bother to do it. So, okay. In any case, the answer is, come on. Well, none of you know the answer? I actually don't remember the answer. That's very nice. Okay, I knew you'd get it. Okay, so obviously, factoring is much harder than multiplication. And, well, for small numbers you can do it, but for much larger numbers, no one knows how to do it. And what Shor showed is that there is a quantum algorithm that takes a number, n, and manages to factorize it in time, which is n to the 3, where little n is just the number of digits that are required to represent the number. And the best classic algorithm takes exponential in n to the 1 over to the 3rd. And the way he did it is by, this is also something on skip. The way he did it is by basically, this is how you should think about quantum algorithms. There are 2 to the n slit experiments. Okay? You have, instead of 2 slit experiments, you can think of a quantum algorithm as a 2 to the n slit experiment, where the different slits, the different possible 2 to the n configurations, send different possibilities to all directions, and they either add up or destructively interfere. And in order to design a quantum algorithm well, you have to make sure that the right answers have constructive interference and the wrong answers have destructive interference. And that's a very complicated thing to do. And so it's a very, very big challenge to come up with new quantum algorithms. So I'll stop here and leave the floor for questions.
Okay, so thank you so much.
classes at 3, now it's 3 and 6 minutes, and we cannot go back in time. I don't know the way, she knows for sure. I don't know the way. But so, one question, one quick question. Yes, my question.
No, your question is much harder to answer, so yeah.
Can you upload the
Sorry, can you
upload the representation to your website?
Yes, but that's not a real question. I can't hear you.
A quantum system can be in a set of possibilities. Is there any possible state which counts the most? I mean, among the set of possibilities, is there a most possible state?
Is there a possible what state?
A quantum system.
Please, quiet.
A quantum system is a set of possible states, possibilities. So I want to know whether there is the most possible state which can turn into an actuality.
No, I mean, there are, so quantum states, as I explained, are just, the number of possibilities is enormous. And there are more possible states which are easy to create. Not all states we can create in any reasonable time. So there is sort of a subset of states which are much easier to create. So these are more possible states.
Which counts different?
Yeah, I think I answered the question. Thank you very much.